Let's talk about the standard light bulb. I have here a 150 watt light bulb at 120 volts, and as you can see, the electricity will come in here, up the copper wire, then through that curly piece of tungsten in the middle, and then down out through this copper wire here, and then out to complete the loop. Well, when the electricity flows through the tungsten, it heats up and radiates visible light. Why does it heat up? Because it has resistance. Well, let's watch this guy in action. And there you go, shining brightly. But it's not shining at 150 watts. Even though it clearly says 150 watts on the light bulb, that was clearly not 150 watts. The reason is it's only 150 watts when run at 120 volts, which is your standard voltage in US households. But my power supply, as you can see, only goes up to, well, right now it's up at 90, but dropping quickly. It'll stabilize around 70 volts. Oh, yep, yeah, it's still dropping. By the way, why is it dropping? Well, because the resistance of the light bulb does change as it heats up. And for the purposes of this lesson, I'm going to assume a constant resistance for the light bulb. But just so you know, in reality, it actually does change a bit. Okay, let's figure out how bright does the light bulb shine when it's run at 70 volts. Well, in order to do that, we first have to define the key characteristic of the light bulb, which is its resistance. What do we know? Well, we know it's 150 watts when run at 120 volts. Well, we know also that power is voltage times current. And the power tells you the brightness of the light bulb. Power is literally the joules radiated per second. Or I should be more honest. Power is the amount of energy, the number of joules per second. And some of that, actually the lesser fraction of that, is radiated as light. And the majority of that is radiated as heat. And that's why these light bulbs, these tungsten light bulbs, are inefficient. You should use fluorescent or LED light bulbs where a greater percentage of the power goes to visible light. Okay, that aside, let's calculate its resistance. Well, this is the power equation, but we also know Ohm's law, and Ohm's law tells us that the current is equal to the voltage divided by the resistance. We can plug in here for current, and then we get power equals voltage times voltage over resistance, or in other words, the power is the voltage squared over the resistance. And now we can plug in the values that we have, and we have 150 watts equals 120 volts squared all over the resistance. And if we just do a little algebra, multiply both sides by R, and then divide both sides by 150 watts. Remember, whatever you do to one side, you have to do to the other side. And then you can see that these guys cancel, cancel, cancel. And what do we have left? We have resistance equals 120 volts squared divided by 150. Resistance is 120 volts squared divided by 150. Well, 120 squared is 14,400 volts squared, all over 150 watts. And if you work that out, it's around 95 or something, but since we're dealing in approximates, let's call it 100 ohms. So the resistance of a 150 watt light bulb is about 100 ohms. Excellent. Now we can figure out how bright it is, or more specifically, how much power it's giving off when run at 70 volts. So at 70 volts, the power equals what? Well, power, voltage squared over resistance, just doing what we did before, and it's 70 volts squared all over about 100 ohms. And 70 squared is 4,900 volts squared over 100 ohms. Volts squared over ohms gives you watts. And that gives us 49 watts. So when I run it at 70 volts, it's 49 watts, not 150 watts. And that tells us it's about 1/3 as bright. 49 is about 50, 50 compared to 150 is about 1/3 as much. And sure enough, I buy that. It's about a third as bright as a 150 watt light bulb would be.